in this video, let us talk about the monotone subsequence theorem. It states that every sequence of real number has a monotone subsequence. So let us prove this theorem. Okay, I have written the hint over here. So first hint would be the definition of the peak of a sequence. What do you mean by the peak of a sequence? So that is what you have to know. Second hint will be the cases, that is finite peaks as well as infinite peaks. There will be two cases on which you have to say on both the cases this holds. Then the theorem completes. So for the case 1, that is infinite case, you would have arrived at the monotonically decreasing subsequence. So you need to show for the finite case also there is a monotone subsequence. That is, you would be getting monotonically increasing subsequence for the finite case. And for the finite case, there is another one hint. You have to use this one. There is no peak after the finite stage, because if it is finite peaks, you obviously know there will be no peaks after the finite stage. So this is the hint that you can use to prove the theorem. Now let us see graphically what does it mean. Okay, this is the peak of a sequence definition. Un is a given sequence. Uk would be the peak of this sequence. That is, it is some element of Un. It is said to be peak if this condition getting satisfied. That is, Uk should be greater than or equal to Un for all n greater than k. So after this kth stage, every element should be lesser than or equal to uk. That is, uk, it's like a bounded definition. You can see this uk would be the element of the sequence itself. So after which every element of the sequence would be lesser than the peak element. Let's understand what is the peak. So if my sequence is like this, let's discuss what is a peak. So I'm having a sequence u1, u2, u3, u4 and so on. So I have to pick an element from this sequence. So I'm telling this is the peak because after this stage there is no element that comes in this line. So I can draw an imaginary line. So since nothing is crosses, so this is my peak. And I'm going to say the second peak is this one, because you can observe again that is no other element will obviously comes into this. If it comes, then this is not a peak. So in this way I'll be getting the other peaks. So you can imagine what are all the peaks comes over here. Yes, this won't come because this is not a peak obviously. So this will be coming because this is the stage, nothing crosses over here. And again this will be coming. So these are the peaks. And if the sequence goes again, so we will be determining what are the peaks comes over here. So next, okay, let's talk about the peak for this sequence. So for this sequence, this won't be the peak obviously, because after this there are elements coming over here. And so for this sequence, this is the peak only when the imaginary line should after this stage no other element should comes after it. So this is my peak, and hence I can say that this is my infinite peak case and this is my finite peak. The proof starts from the definition of a peak of a sequence. So note that uk is greater than all the elements beyond this uk. So uk is greater than all the elements beyond uk means, so after uk there is no other element which would be greater than uk. So that is what basically in peak is all about. So it arises two cases, that is no peaks or finite number of peaks. Second case would be infinite peaks. So we will see what is the case 1, infinite peak. So let us have un to be having an infinite number of peaks. Let the peaks be called as ur1, ur2, ur3 and so on. So there will be infinite number of terms. So we have this one, that is ur1 is greater than equal to ur2, which is greater than equal to ur3, which is greater than, and so on. It has infinite number of elements. Why I have written greater than equal to? Because that is by the definition of the peak. So if suppose if in the middle, if I am getting less than or equal to, suppose if ur2 is less than or equal to ur3, then that is not a peak obviously. ur2, it's not a peak itself. So that means it is not a peak, but we have took only the peaks, that is infinite number of peaks we have taken. So obviously ur1 should be greater than equal to ur2, which is greater than equal to ur3 and so on. That is by the definition of the peak. Hence we have said this un has a monotonic decreasing subsequence when it has a infinite peaks. Now we will look at the no peak case or a finite peak case. So both are same. So let us see this case 2. So now our case 2 is finite number of peaks. Since it has a finite number of peaks, I already told that you have to use the hint called there is no peak after a finite stage. So let me call that u1 ur1 again ur2 and so on. So in the previous case it goes on because there is an infinite number of peaks, but here it stops. So these are my peaks, the peaks. Okay, so if this is a peak, then I am going to say, let us call S1 to be Rm plus 1. That is the immediate element after this URM. I am taking US1. That is the next element after this. I am going to collect this element, and obviously this is not my peak because I have collected the peak already. So this is not a peak element. So now I can say this is not a peak element. Then there exists something called S2 in n, natural number, because these are all note that this is a natural number all. Okay, so this is also a natural number. So this is also a natural number. There exists S2 because after this there is no peak. Okay, after this rmth stage there is no peak. So I can say that S2 will be there and there is no peak. So I can say S2 is greater than S1. No peak means US2 will be greater than US1. So this is the negation statement for the peak. Okay, so since US1 is not a peak, US2 is also not a peak. So I can say US in a proper way, US1 is not a peak. Hence there exists S2 in such that S2 is greater than S1 with US2 is greater than US1. So this is how I'm going to prove this one. So in this way I'm going to take another element called US3. So here I can say, since US2 is not a peak, again by the not a peak definition of a peak, I can say there exists S3 in n such that S3 will be greater than S2 such that US3 will be greater than US1. So if it is a peak, then it will be less than or equal to. So it is not a peak, so it is greater than. Okay, so in this way I can say that proceeding with us we obtain Si such that Si will be lesser than Si plus 1 such that USI will be lesser than USI plus 1. Hence I am going to collect in this way and it goes on. Now my sequence I have collected is like this: US2, US3 and so on. So in this way I am going to collect, and hence I am getting the monotonically increasing subsequence. So I think the finite number of peaks alone should have taken a quite long time, but this is simple when you know the definition of the peak of a sequence. So the idea is simple. I'll just say what is this all about for the finite peak case. So the simple idea is I'm collecting all the peaks I'm collecting all the peaks at first, that is this stage. So I have collected all the peaks, and after this there is no peak because it is a finite number of peaks. So this stage can be some 1000 factorial stage. So it can be any number, it can be 10th stage or anything. So after this there is an element which is not a peak. So if this is the last peak, then there is no peak after this. So I am going to say collect this element and then the next element which is bigger than this, then again, and goes on. So in this way I am going to get the monotonically increasing subsequence. Hence I have proved this theorem for both the cases.